straight over to Peter for his presentation, and then we'll take questions at the end. So if you do have questions, please pop them in the doc in the meantime. Peter, we'll hand over to you.
Thank you. I'm going to share, oops, see what I'm doing. Can people see these slides, he asked?
Yes.
Wonderful. Thanks so much. Thanks very much to Javier. And I want to say that I've learned so much about Whisper and automatic speech recognition from talking with both Javier and the team up in Norway. They're a really great team. I'm going to really focus on kind of some very exploratory, non-production ready uses of Whisper inside Stanford Libraries. And I should say this is not yet a formal project. We've been kind of experimenting with this, and we know we can learn a lot from folks all over the world. I wanted to show you some examples of what's going on here. And of course, I don't have to motivate, I don't think, the desire to take audio or video with an audio track and turn it into text. We have to do this for accessibility reasons as we face a changing legal landscape, for those who use screen readers, who have hearing disabilities, or just feel more comfortable watching a transcript. We also have a need to do this because a lot of folks on our campus do a lot of text mining, and there's an incredible wealth of information inside oral histories or video recordings that just isn't tractable until it gets turned into text. And then finally, of course, there's this notion of metadata. How can we describe objects better? And one of the ways we can describe them better is through using linked open data. And one of the ways we get linked open data is to run entity recognizers on text. We don't have text until we have run ASR or speech to text on our collections. So these are kind of the things that are pushing us forward. And it's a great time to be interested in speech to text, because we are in this moment where, and I swear I'm not going to talk about GPT, but I want us to focus on the T in GPT, which of course stands for transformer. We are in this moment of transformers, a particular form of math that is having an enormous impact across all sorts of domains. It's having an impact in synthesis, producing text. It's also having a huge impact on taking speech and turning it into text. It's even going to affect, I believe, handwritten text recognition in terms of the new updates to the Transcribus core algorithm, as well as competitors such as OCR. We are not going to go into transformers mathematically on this talk because it's above my math competency, but I think what's interesting is the way that in previous convolutional networks, we sort of looked at local areas of data. And that what's interesting about transformers is that it really allows us to look at the whole thing at once. And this is articulated in the famous paper, Attention is All You Need. I put up a very simplified, I borrowed a very simplified diagram of convolutional neural networks on the top versus transformers at the bottom. There's a trillion implementation details which make this diagram more useful as a schematic than any kind of actual capture of what's going on. But the idea is, how can these models how can these algorithms start looking at more data all at once? And once it does so, it's much more able to look at something very complex like human speech. There is a paper behind Whisper. You can read it on arXiv. But I think what's kind of interesting about Whisper is looking not only at the math that's behind it, but the context in which it's in. Whisper was trained using this algorithm on an enormous amount of data. It's allegedly 700,000 hours. It seems very clear that it was at least in part YouTube captions, which is both good and bad. One of the things I learned from my colleagues at the University of the National Library of Norway was that Whisper is very interesting in that it can sometimes fail to beat artificial benchmarks. But when you actually start using it in real world collections, it does better than you think, and probably better than a human in many cases. And it does not have to be trained on a voice in order to produce results. So that's why we call it zero shot. It's never heard a voice before and it's able to transcribe it. I said before, it's not just the math, it's not just the algorithm, it's also what models OpenAI very generously produced. There are many models that OpenAI released along with a code. They run from very small models that are run on your laptop, all the way to enormous multilingual models that require advanced GPUs. As I said, they're trained on an enormous amount of information. It's interesting that some of them are English only, some of them are multilingual. We'll come to that in a second. And of course, like anything else, it's speed versus accuracy. Javier mentioned that Whisper understands speech through images, and this is true. It's a really bizarre, it seems like the last thing that will happen on planet Earth is we will start will be an analysis of a ping representation of data. Everything, the tools for images are so powerful, whether it's convolutions or transformers, that we are sort of compelled to turn everything into a ping and then analyze it. So for those of you who have heard about Riffusion, R-I-F-F-U-S-I-O-N, a music generation model, my understanding is that's using a diffusion-based model like DALL-E to produce a Mel spectrogram that then turns into music. So the image analysis and the image generation is so powerful that everything will become an image in the future, whether you want it or not. This includes your voice. So Whisper sort of splits your voice into chunks, converts it into this interesting visualization called a Mel spectrogram at the bottom left, puts it to an encoder, and then the decoder predicts the text that should result. There's a lot of interesting internals of Whisper about how to decode in this encoder-decoder network. Most of this is sort of not, it's useful to keep in mind as you start chasing down problems or edge cases. But there's a couple different ways, both greedy and what's called beam search, to sort of decode the language and take it into text. But I think what I want to focus on here is just the possibility that everybody on this call can actually start playing around with Whisper on like a $900 MacBook Air or a $500 Dell. A lot of us would use the reference implementation, which is really only tractable if you have an NVIDIA GPU. It's a great reference implementation. That's the first link here. It is updated all the time. Bugs are filed, bugs are fixed. That's really exciting. This is not something that they just put out and then are ignoring. A lot of folks are also excited by this independent researcher, Gregory Gurganov, who has put out something called whisper.cpp, which was written in a lower level language and designed to run on CPU. There are two interesting things about this. It means that you can run it on a laptop with no GPU at all. It'll still work pretty well. There's also an interesting situation, we're going to see this in a second, where there's a very intricate optimization for linear algebra, I believe, that makes it run very quickly if you have an Apple Silicon machine. Confusingly, although Gurganov's code was originally designed to eliminate the need for an expensive $3,000 NVIDIA GPU, he's actually also added in GPU acceleration. Another thing I want to mention is there's a great, this is the last link at the very bottom, a totally other person has put together a GUI for Windows, which uses Gurganov's GPU-less code. Or in some cases, we'll even use the iGPU inside a laptop. So for those of you who are in Windows laptops and just want to play around with it, take a look at this third link here, const-me, their implementation of Whisper, which uses Gurganov's Whisper CPP. And as you can see, anybody can use this interface. It will automatically download the model and produce a transcript. It's fun just to play around with this. Okay, what does this look like? Let's go with the reference implementation and let's take a look at an actual oral history from Stanford's collections. On the bottom, you're seeing a visualization of the usage of an NVIDIA Quadro board. So you can see that I'm using the large model in this test, and that means that I'm using over practically 12 gigabytes of VRAM on an NVIDIA GPU. That's the orange line. The sort of light blue-green line is the not how much VRAM, but how much utilization it's taking of the card. So you can see how quickly this is going. It's much faster than real time. And that's pretty exciting to be able to do that if you have one of those machines around. But not everybody has those types of machines. So what I'm going to do now is get out a full screen. And what I'm going to try to do is take us to terminal. I'm just going to confirm with somebody like Neil that you can see a terminal on the screen now. Is that okay?
Yes.
Thank you. Okay. What I'm going to do is I'm going to I'm running a MacBook Pro here, and I'm actually going to take the same one that you just saw. You can probably, which is an oral history about the experience of African Americans at Stanford. Zoom's video compression is making it probably so that you can't see this very well, and that's the point. It's going much faster than real time. It's a MacBook Pro, but it doesn't have a big NVIDIA board. It's just, you could do relatively similar performance on like a MacBook Air. This is using the Gurganov whisper.cpp. So in the past, when we've talked about transcription, we've said, well, we're going to have to send it to a vendor, and they're going to take all sorts of time to do it. As you can see, this is very clearly faster than real time, and it's happening right on the machine. No data is leaving Stanford's network. Other things that are kind of interesting is that with Gurganov's implementation, which does differ a teeny bit from the NVIDIA implementation, I can do something like ask for the, let's see where we are here. I can ask for an view of the, as long as I paste the right code. I can ask for a visualization of the confidence in each word, or each sort of set of tokens. Or actually, in this case, what I'm doing, I apologize, I'm actually showing special tokens, which are the beginning of speech. This is kind of a behind the scenes thing that may not be meaningful to you, but what you can see is it's inserting things like beginning here. These tokens can be useful in debugging cases where Whisper is not quite giving you the right results. And they're normally hidden. They're not a part of the transcript, but it can be interesting to see, well, when is Whisper interpreting silence and when does it think that speech is beginning? The other thing I wanted to show you was the one I started to talk about, which was confidence visualization. So let's clear this. And let's show a color-coded visualization of how confident the Whisper model is in what this person is saying. I'll stop it here so we can take a look at it. In this case, green means it's very confident about the words, and red means that it's less confident. And that may be just dependent on the recording quality, the dialect or sociolect of the person who's speaking. But as you're trying to debug problems with this, it is kind of interesting to think about what it is confident about and what it is not confident about. So that's Whisper. Let's make this a little bigger and talk about Whisper in the context of human transcription. One of the oral history projects that I decided to evaluate Whisper on has actually already been transcribed via human. And you could say, well, that makes it a poor choice. In fact, it makes it a really interesting choice because we have a great validation set already. On the left is a transcription of that recording by a human. On the right is through Whisper. And some of this is kind of Stanford specific, but you can see that it is getting wrong. I'll move my mouse down here. You'll see at the second paragraph, she's talking about mem-aud and mem-chew. And mem-aud is memorial auditorium. And Whisper does not quite know how to spell that, but a lot of people don't. You also notice if you look at that same paragraph, Natalie Marie Street, or excuse me, Joanne Johnson she says mem-chew first, which is Memorial Church, and then she corrects herself to say Memorial Auditorium or mem-aud. The human transcriber elided that error. They took out the fact that she said Memorial Church or mem-chew first, and left in the fact that she said Memorial Auditorium. So the notion of perfection is really interesting. You have to sort of define like, well, what did we want? What she meant to say or what the editor put in. I don't think there's anything wrong with what the editor, the transcriber did on the far left, but it is interesting to think about what you're going to get out of a transcription model, which doesn't know when humans are making mistakes. There are a lot of great output formats for Whisper. If you just want raw text for text mining, you can get that. You can also get, of course, these very important subtitle formats like VTT and Subrip is mostly used for pirated movies, but it is supported here. Let's talk a little bit about problems in Whisper. So it's a great implementation. It's a great model, but there are certain cases where it goes a little pear-shaped. There are situations where it can hallucinate out of no audio or noisy audio. It can produce the wrong signal. There's also a fascinating case I found of false diarization. We're going to talk about diarization in just a second, where it will start to impute speaker labels, which would be cool, but they're not actually the names of the people who are talking. And this is its origin in YouTube subtitles, where sometimes the name of the speaker is given. And there's definitely a problem sometimes with repetitive loops. So let's look at that for a second. The first one of these, which is hallucinations. Hallucinations can happen in periods of no speech. And there's a couple levers you can pull in the various implementations to help make sure that doesn't cause problems. What I love about this, I think this is from a blog post that I cut this out from, is you can see with base is the smallest model, and then small, medium, and large get bigger and bigger. Actually, tiny is the tiniest model. The hallucination grows better, more, it will hallucinate more with a more robust model, which is kind of an interesting problem. So it has more possibilities to imagine in sort of static or unclear speech. Here's an example drawn from an oral history of looping, of Whisper getting caught in a loop. The speaker is not saying this phrase over and over again. There are a couple levers you can pull. You can switch the model size, which will usually avoid a problem in that particular area. And you can also adjust the decoding strategy. This looks bad, but I would say it's very clear when this starts happening. So in a sense, a quick human review of this would catch a hallucination or a repetition that it happened. Javier talked a lot about Whisper and multilingualism. Here's a visualization of all of the languages that are present in here. It does not, as he mentioned, go to languages such as Sami, but it does capture a lot more than other models that have been public released. And there is this really fascinating situation where I can feed it a video of me speaking a different language on the left. And I can either ask for the transcription of what I'm saying on the left. This was in a talk in Uppsala, or I can ask it for a translation of what I'm saying. And it's all part of the same model. Whisper thinks of this problem as sort of linked, that I've either got a Mel spectrogram of speech and I need a text representation of that, or I want a translation of that into another language. The translation is really good, and at least to English. I haven't tried it other directions. So that's another thing to think about for accessibility reasons, or if you have a collection in which you think there might be both Spanish and English speakers who are interested in that collection. We also tried this on German. What I did here was I took the time to visualize the delta between the human transcription of this is some Nuremberg trial stuff we have at Stanford. On the left is a human transcription of this, and on the right is the large multilingual model set to German explicitly. I've listened to this recording. Frankly, it's actually kind of hard to tell what's actually on the tape. It's a I guess early 40s tape. What's being spoken on the tape is a kind of German that is very old. I mean, it's obviously 90 years old, 80 years old, and it's from unfortunately a Nazi. So it's not like the German that probably Whisper was trained on. And so I think there are some cases where is it Fleelich or Dichle? It's really hard to tell on the tape. It's approaching human quality, though, I would say. I wanted to talk quickly about another interesting area of diarization. I mentioned diarization as kind of a problem where sometimes it would start inserting names that don't exist. But more broadly, diarization is the idea that you've got Natalie Marie Street interviewing somebody, you've got Joanne Johnson, the respondent. There's a question and answer in that oral history about being Black at Stanford. And it would be great if we could pull that out. It would be great if we could somehow get those labels, and whether we're going to eventually go to XML or we're going to do whatever. And that's called diarization, knowing when somebody's speaking and optionally sort of inserting labels that characterize that. It turns out Whisper is not good at this because it is so good at just understanding the slurry of sound and sort of visual representations of sound and producing text, that the notion of listening carefully for differences in intonation is just not what it is good at. So the way people tend to solve this is to load other tools into a workflow. And here I've linked a couple interesting GitHub projects that use other packages, such as pianote.audio. There's a bunch of people use that. Some people use TitanNet. And the whole notion is here, we've got all these speakers on the tape. Let's go ahead and characterize their voices into a vector space. Let's create an embedding of what their voices sound like. And then let's try to sort of cluster them and then say that this is the interviewer and this is the respondent. None of this stuff is perfect. One of the interesting problems with Whisper is that its time stamping is not it's okay, but it's not great. It doesn't have like that level of precision where somebody stops talking and somebody starts talking. And so oftentimes the first thing people have to do is to make time stamping way more accurate. And then secondly, do the embedding trick to kind of create characterizations of the voices and have the voices separate well. Do any of us really think that this is optimized for the diversity of North American English? No. I think a lot of this has to be, this is an area of growth for both Whisper and for tool chains that involve Whisper. I'm sure there are going to be challenges down the road, but I think it's something that a lot of us who care about transcripts are interested in. Let's zoom forward so we can get some questions here. I think this is basically what I wanted to talk about. So I'm going to go ahead and stop sharing my screen. And that way we'll have just a chance for discussions from the folks in the meeting. Thanks very much.
Thank you so much, Peter. That was great. Any questions for either Peter or Javier? So while
I have a question. Sorry.
Go ahead.
I have a question about the performance of if you all have seen any differences, or if it's been tested on well, I guess we got a little bit of the historic, but I wonder if, since libraries and archives have so much historic content, if like the historic context, how that is interpreted with these contemporary tools. Are there experiments, sort of thinking about that piece of performance?
It's a great question. I can think of all sorts of, historically things that would inflect this. You can think of, the kind of what we call the mid-Atlantic accent, things that people don't really use anymore, but were very popular in the 20th century, especially in recorded media. You can also think about, just as we had a local context at Stanford, Stanford alums will sometimes call something mem-chew or mem-odd, and there's not enough signal in there for a whisper to have been trained on that. So there are probably hyper-local contexts in which the results are going to be bad. There's also the influence of recording technology. Like if you were doing this on like wax cylinder voices, like the characteristics are probably very different than YouTube in terms of sonic quality. So I think there's a lot of, one of the things that's great about the work at the National Library of Norway is retraining Whisper, pushing weights in new directions to do things, but the same could be true sonically, right? Where you could sort of try to say, we have a bunch of 1930s stage plays. People are talking these very stagey artificial voices. Could we push Whisper in a direction where it could start recognizing those in a better way?
In our experience, we haven't run any thorough testing on historical recordings. We have the whole archive of radio broadcast in Norway dating back like 80 years or so. There is one sample that we usually use when we talk about this technology. That's the Thora Meyer inaugural speech in the city of Moiran, I think it is. And it's actually kind of good, even though the quality of the sound is not very good. The language has obviously changed. The result is really good. One of the good things that also Whisper tells you is the ability to prompt the language. So Whisper models are sequence to sequence. So there is an encoder taking in all the audio, and then there is a decoder, which works like a GPT model. So you can prompt the model and help the model produce, for example, the correct spelling of people involved in the conversation. So when you mix that into the generating process, because you can give it the model a little bit of context, then the outputs are much better than when the model has to guess how all the people's names in the conversation look like. So there are still a lot of things that can be pushed in the Whisper models to get it even better.